welcome you to our fourth and final Allied event of Spring 2025. We're honored to have Dr. Michele Mele join us. He's a research fellow at the University of Sannio in Italy, an award-winning author, and was knighted as a Cavalier of the Order of the Italian Republic. His presentation, Beyond Sight: How Blind Scientists Model the World, explores the legacies of brilliant blind scientists who reshape science through their perspectives. Dr. Mele builds on their legacy by sharing his work in combinatorial optimization and accessible STEM education as a blind mathematician. Let's get started. All right, welcome Allies of Allied. I'm really happy to present our fourth and final event of the semester for our Spring 2025 Allied Talk series. To wrap it up, we have Dr. Michele Mele joining us from Italy. Today we will be presenting on Beyond Sight: How Blind Scientists Model the World. He is joining from Italy, like I've mentioned earlier. It is 9 p.m. over there, so we appreciate you for joining us at such a late, awkward time. Aside from being a dear friend of Dr. Mona Mankara, he is a research fellow at University of Sannio in Benevento, Italy, with focus on combinatorial optimization. He is an award-winning author, and he also is a musician involved in folk music. Today, our American Sign Language interpreters are Lucy Annett and Wendy Jalen. And with that, I'm going to introduce Dr. Michele Mele and his presentation.
Okay, can you hear me?
Yes.
Okay, thanks. Good afternoon. It's a nice windy evening here in Salerno. I am Dr. Michele Mele, as you said. I am a research fellow at the Department of Engineering of the University of Sannio in Benevento, Italy. And my research spans different fields of mathematics, from combinatorial optimization, mainly scheduling and timetabling problems, slide 2, to mathematics education and the history of science, with a particular focus on equity, inclusion, and accessibility of mathematics and science more in general. As a blind scientist, I'm very passionate about everything related to inclusion in STEM, and today we'll have a journey together. We'll have a journey through different branches of mathematics and different periods and countries to understand how the work of blind mathematicians and blind scientists in general throughout history has changed, and how it has changed our world. Next slide. Everything starts in Thurlestone, a little village in the mountains of South Yorkshire. It's the place where it has been recorded, the birth and the baptism on January the 20th, 1682, of Nicholas Saunderson, son of Anne Briggs, a tailor, and of John Saunderson, an exciseman, mainly actually a local tax collector for the British government. Nicholas Saunderson is today remembered as the first known blind scientist in history, a mathematician that lost his sight at the age of 1 due to smallpox. But I always say it's context that determines this ability and not a handful of missing cells. What happened is that his father, in an era where, of course, there were no computers, there was no braille, taught him the alphabet, guiding his hands on inscriptions on the graves of the graveyard that surrounds the parish church in the little nearby town of Penistone in South Yorkshire. It is an act of trust that erased every self-loathing, every form of pietism, even in the nearby community. Slide 4, next one. And convinced Nicholas Saunderson that despite blindness, he could achieve what he wanted. He attended first Penistone Free School and then Penistone Grammar School. The main building of Penistone Grammar School today is named after him. And became not only fluent in English, of course, and in French, but also in Old Greek and Latin, acquiring a big passion for Euclid and a good hand on the wooden flute. In these years, he needed someone to read aloud for him, and among the people who did it, there were even two members of parliament who did it for free. One is Richard West, Esquire of Underbank, a nobleman and poet, and the other is Dr. Nettleton of Halifax, working in Sheffield, known by many doctors of one of the earliest proto-immunologists. Slide 5. In those years, particularly in the 1690s, Nicholas Saunderson created the first ever device to teach maths through the sense of touch. John Coulson, a colleague of Saunderson's, a mathematician himself, called it the table of palpable arithmetics. Today we call it Saunderson's tactile table. And in the next weeks, this month anyway, you'll find on Scopus and Scholar, it will be out in a few days, an article I wrote with engineer Gennaro Siciliano of the Synapsis Center of the University of Naples, Federico II, in which we rediscovered through ancient documents the functioning of this device and its influence, because many devices that we use today, like the Cupereth or the Taylor slate, so even things used even by sighted people, descend from this tool. It was a simple instrument. Just imagine a wooden square of about 1 foot, 30 centimeters, for having edges of about 1 foot. It was divided into 100 smaller squares by thin wooden stripes glued on its surface. So imagine a 10 by 10 grid of smaller squares that I'll call them digit squares. Each digit square had 9 holes in it, arranged in a 3 by 3 grid, just like the tic-tac-toe field. Now, when sighted people learn to write and to do basic operations, they learn to line up digits on columns, the units, then to their left the tens, and then the hundreds and the thousands, and so on, writing numbers on rows and lining up digits on columns. Despite being blind and not being able to learn to write with pen and ink, Saunderson, following a different path, arrived to the same conclusion and created a non-ambiguous form of coding numbers in the same way. To do this, he wrote numbers on lines, lining up digits on columns, and we go to slide 6, with the coding of digits. To do this, he needed a non-ambiguous way of coding digits. He did it thanks to 2 sets of pins, distinguishable by the heads. A set of large-headed pins and a set of small-headed pins. Here you'll see 4 digit squares representing the coding of 0, 1, 2, and 5, respectively, top left, top right, bottom left, bottom right corner. The asterisk represents the small-headed pin and the circle a large-headed pin. He represented 0 by a large-headed pin in the middle hole. So in the central line of the central column or row of the 3 by 3 grid, depending on your philosophy. And with a small-headed pin, by a small-headed pin in the same place, he represented 1. He represented 2 by a large-headed pin in the middle hole and a small-headed pin just above it. Okay, it's the bottom left one, sorry. What happened is that he created all the other representations, all the other codings of the other digits from 3 to 9, just moving the small-headed pin clockwise, leaving the large-headed pin in the middle hole. So he represented like 4 with a large-headed pin in the middle hole and a small-headed pin just to his right, or 5 with a large-headed pin in the middle hole and a small-headed pin to the bottom right hole, or 9, completing the root with a large-headed pin in the middle hole and a small-headed pin in the top left corner. We go to slide 7. So it is a basic operation. This is not the whole table because it would be dispersive. It would be too big to represent and the pins would be too small. This is just the corner, the top right corner of the table, obtained crossing the top 3 rows and the most right 3 columns. This is a basic operation of 52 plus 68 equals 120. We have no clear indication from sources whether he invented even a way to code operations, but we know he had he had a great memory. From the sources we have, we know that he could stop computing on this table and restart with no falterings, doubt, or mistake 7 or even 8 hours later. So he had a very, very good memory. One could say, well, he could represent digit K with K pins. That would be easier, but it's time consuming and quite non-optimal. Imagine you're blind and you're touching, as this device requires, a row on which 1 million is represented from right to left. You'll find an empty digit square, then another empty digit square, and so on until the 7th from right column, where a solitary pin will tell you that there's a number coded on that. So you see, it's quite time consuming, not very efficient, this different method. That's why probably he devised this coding method. He even invented a version of the tactile table for geometry with no digit square, just a table of the same dimension full of holes. He used to put pins into the holes and used to drive a thin silk thread through the holes in the heads or around the pins, just with the modern geoboard, which is another instrument descending from his intuition. You see that despite being blind, he managed, and I would say even thanks for the fact he was blind, he managed to create instruments that are still now useful for the blind, and not only for the blind community, because the geoboard is even used by sighted kids when they have to learn geometry, at least here in Italy. An important thing to say there is that Nicholas Saunderson, and we go to slide 8, was completely self-taught, and after a brief spell at a descending academy where he didn't like the way maths was presented, with geometry on a pedestal well above all the other subjects like algebra or fluxions, he went back to Thurston and just went on to study by himself, with people reading aloud for him. We have scarce indications of his life in this period, but we know that in 1707 he went to Cambridge, not to study at university, but to teach. And after some weeks, the university eventually accepted him, giving him a role that we might today identify with teaching assistant. They gave him even lodgings at Christ College, one of the oldest colleges, founded in 1436 and renamed this way in 1505, a beautiful Gothic building, and even access to the immense library of the University of Cambridge. The point is that this blind guy coming from the north needed someone to read aloud for him, and it was not an exploited undergrad or a PhD student to read for him. It was the location professor himself. So the person having the most important chair in the mathematical world, the same chair that before William Whiston was the name of the then location professor, had been in the hands of Isaac Barrow and Isaac Newton only. Whiston, the third location professor, spent countless hours reading aloud for Saunderson and discussing the latest developments of maths, and not only with maths, even with optics, astronomy, and other subjects. And so, slide 9, we have here a little scandal, the most important scandal in the history of British universities. William Whiston was suspended. Yeah, William Whiston was suspended from the location chair because he was not only a mathematician, but even a translator. He could speak 7 languages, and even a theologian. And it was because of a controversial theological publication that he was suspended in the summer of 1711. The whole university could count on people like Newton, Taylor, Coates, Flamsteed. There were a lot of great mathematicians at that time, even Colson that I already mentioned. But the University of Cambridge chose a self-taught blind mathematician as the next location professor that gave him the mandatory, honorary, and deserved degree he needed to get that role. And on November the 20th, 1711, with just 4 votes out of 16 against him for another candidate, so with 12 out of 16 votes in his favor, it's quite a complicated mechanism, but let's say roughly 3/4 of people for him. Nicholas Saunderson was elected as the next education professor, the fourth after just Barrow, Newton, and Weston. A couple of months later, on January the 21st, 1712, Nicholas Saunderson delivered his first speech as education professor. A powerful message. He identified in the speech, in pure Ciceronian style, maths as the main core of our understanding of the universe, not only geometry, the whole of mathematics. The little kid who learned the alphabet touching gravestones had just become a champion of the Enlightenment. In 1714, he was even nominated in the Longitude Board, and in 1719, he became a full member of the Royal Society. He kept the Lucasian chair until his death, out of scurvy, in April 1739 at the age of 57. Slide 10. Well, this is an important point. He could abstract from the concreteness of geometry. He was very well read in many different subjects, not only in maths, not only in science. He was a workaholic who could teach for like 7, 8, 9 hours a day. Had a lot of important students, biologists, doctors, and mathematicians, and archaeologists, and more. But the most important thing is that he was very good at teaching, even optics. We have sources saying it's incredible how a blind person who has no memory of light can teach optics in such a rigorous and yet clear way. His mathematical results, all published posthumously and dictated to John Colson, who became the fifth Lucasian professor after him, a dear friend of his, are about the following subjects: algebra, infinite series, and probability. Everyone knows the inverse of the Bernoulli formula, every mathematician, and the Bayes theorem, of course. Those are, both of them, intuitions by Saunderson, who was the first one to prove them. And same for the D'Alembert theorem, the D'Alembert criteria for infinite series. It was a Saunderson's theorem, actually. It was proven decades before the Frenchman published it in Berlin. But the most incredible case is in algebra. Everyone in this room, and not only in this room, even like in secondary school, could calculate the maximum common divisor in between two numbers. Okay, at least if the numbers are not giant. This happens because mentally we operate an algorithm created by Nicholas Saunderson. The previous algorithm was much, much longer, needed pen and ink and paper. It is thanks to a blind person that we have saved so much ink and so much paper. But in particular, it's no surprise that it's thanks to a blind person that we have this algorithm and many others, as I told you. It's very important to remember this. He could abstract. This is the main word from this talk, from this seminar. He could abstract from the concreteness of geometry and fly higher in more abstract fields and produce maths, not only despite blindness, but even, I would say, because of his condition. In those same years, slide 11, another great mathematician was born, even a more prolific one, a Swiss man called Leonhard Euler. The German pronunciation should be Euler, but out of clarity, I'll just say Euler. After getting a degree in Basel, his hometown in the northwest corner of Switzerland, he moved to St. Petersburg, where he returned even after a long 25 years old spell in Berlin at the court of Frederick II of Prussia. Slide 12. He lost his sight from one eye and rapidly even from the other one, from the spring of 1735. We don't know how. An illness, stress out of an astronomical measuration, we don't know. We have multiple hypotheses, but we don't know. We know that he was practically completely blind when in 1736 he solved an apparently pointless problem for which he founded an entire branch of mathematics. Sadly, today, the city of Kaliningrad is a militarized enclave of Russia between the Baltic Sea, Lithuania, and Poland. At that time, it was a German city where even philosopher Immanuel Kant was born, called Königsberg. The river Pregel divides the town in two, and two islands divide the river at some point. From the major of these two islands, the biggest one, there were four bridges, two connecting it to the left bank and two connecting it to the right bank. From the smaller, one bridge to the right side and one to the left. And there was a seventh bridge connecting the two islands, the famous seven bridges of Königsberg. People at that time, I'm not joking, this is, I can prove it through documents. People, after Mass, particularly on Sunday, had like the hobby of looking for a path that started and ended on the same bank of the river Pregel and crossing each bridge exactly once. The problem was suggested to Euler. And he created graph theory to solve the problem. Yeah, I'm not joking. Next slide, should be 13. He identified land masses with vertices and bridges with edges or arcs, like someone sometimes calls them in continental Europe. I say edges. So you see, he created not only the first graph, but the first multigraph, and even the concept of degree of a vertex, the number of incident edges or arcs, if you want, who touch it. It's very important to notice that he could abstract from the concrete case. People were like focusing on the shape of the islands, the twists and turns on the river. No, he identified a general solution in graph theory, and he founded this combinatorial problem with the famous theorem of the seven bridges, in which he showed that there was no such path and identified the conditions in which this path could have existed. And it's all dependent on the degree of the start and end point of the path. We use graphs, next slide, for everything, literally everything today, from like social media profiling to, of course, our connection of today. We are now all connected through a spanning tree, which is a particular subgraph of the complete graph that connects the whole of us. And for transport, but even for like adverts, search engines, sorry, and even for finding terrorist cells around the world with clustering problems. We use graphs for literally everything. Even we, my research group, when we work on scheduling and timetabling problems, like many other research groups, transform them into graph problems. And everything started thanks to the abstraction ability of a blind person. Next slide. A person once told me more than once that blind people cannot understand visual beauty. Well, the most beautiful mathematical formulas, considered as such by like 99% of all scientists around the world, came thanks to another theorem by Leonhard Euler. In 1748, during his Berlin years, he was almost totally blind at that time. We would say legally blind today, more or less like me. He was working on trying to find a connection in between two seemingly completely unrelated topics, exponential functions and trigonometrical functions. He came up with the famous Euler equation and its neighbor, the Euler identity, which is considered the most elegant and beautiful equation of all time. It includes the three most famous numbers constants in mathematics, I, the imaginary unit, pi, and e. And of course, 0 and 1, the basis of computational mathematics. And this is thanks to the abstraction power of a blind person. Next slide. Today, Leonhard Euler is considered one of the 4 greatest mathematicians of all times, together with figures like Archimedes, Carl Friedrich Gauss, and the already mentioned Sir Isaac Newton. He left us 868 original publications plus some pamphlets, almost 900 original publications. And he became even more prolific as the darkness came into his eyes, a powerful proof of the ability of producing maths, of the abstraction ability of how blind people model the world, even yet again without sight. Next slide. They have not been an exception, though. There have been. Yeah, I know someone has raised her hand. Yeah, there are and there have been blind scientists in history. We named Euler, we named Saunderson, but there have been many others. Among the living ones, the one and only Mona Minkara is sitting there with you. And there's Damien Corrigan, one of the minds behind the quick test for sepsis and for COVID-19. John Metcalfe, a pioneer road engineer. François Huber, the father of melitology, the study of honeybees and their life and production, and many, many others who not only produce maths despite blindness, but even because of blindness, because they could follow different mental patterns and even different material patterns thanks to modern technologies, referring to the more modern ones particularly. This is one of the reasons why we need more people with disability, with visual impairment, blind or visual impaired, if you want, in science. And being the, how can I say, the less important of this community, I will love also take this occasion to tell you a bit about my research also. Slide 18. I work on combinatorial optimization, particularly on timetabling and scheduling problems. And my first approach with this subject was with this problem. Today, people with special needs, so not only blind people, but even people with reduced mobility or deaf people, have some troubles traveling independently from other people, like autonomously, by their own. And this is because there are rules that are generally ignored. Next slide, 19. Important organizations like the ICAO, the UN, or the IATA have produced, even in synergy, rules to follow for creating an accessible service. I can't stress enough that these rules are generally ignored because airport managers maybe think they can save money and hire less people for conveying this service, using less people. These rules can be seen in 3 points. 3, let's say, major rules. First, a person with special needs, whether this person is arriving at the airport to take a flight, or leaving a flight to go to the city, or just transitioning from one flight to another, has to be accompanied by the same person throughout his or her journey throughout the airport. Okay? Generally, they are like passed from one person to another, which is very confusing. Second, the airport should, this is very important, this is another of the rules that is generally ignored, should allow the passenger with special needs who requires assistance to choose a language, and the person who assists the passenger should speak that language. English is generally compulsory, but there are so many others widely spoken languages that are generally or should be included in the list. third point is that, of course, workers' rights should be preserved and respected. Not only the length of a work shift, but even the rotation in the roles. These rules, again, are generally completely ignored or partially ignored, where people who organize this service think it's good for the airport. So I decided to try to model this problem with mathematics. I thought that a decision problems, next slide, should be the number 21, right?
Yes.
This problem could be modeled in a mathematical form as a variant of a classical problem that was actually introduced in Boston in the 1950s, the so-called fixed job scheduling. Of course, our jobs are the accompaniments, and they are fixed because we have fixed arrival times and leaving times, departure times for the passengers in all three cases. The start, the end of the mid part, the transitioning part from a flight to another of the journey. And of course, you can imagine that workers are not all the same. We should consider them differently for the language, at least for the languages they can speak. So they are divided into classes. I'm not saying some are better than the others. They just speak different languages and have different flexibilities. So they are divided into classes. And we have here, I modeled the problem with two sets of Boolean, or binary if you prefer, variables. X superscript I line. I use math speak in reading formulas. I hope it's not a big deal. X with superscript I and subscript JK is the first binary variable set. It equals 1, each one of these variables, when worker K belonging to class I accompanies passenger J, and 0 in all other cases. And the Y variables with subscript IK, when K belongs to class I, is actually used in the model. Okay, we have two sets of binary variables. Such a complex problem gets modeled in slide 22, just these few lines. The lower line, the bottom one, is just saying us what I told you in the previous slide. The top is the objective function. We want to minimize the people needed to complete all the tasks, all the accompaniments. And we have three sets of constraints. See, such a big problem reduced to 3 lines. This is the beauty of mathematical modeling, the power of mathematical modeling. The first set of constraints is, we call them variable upper bounds, are merely technical ones who link the two sets of variables. The bottom one, so the second from bottom line, is a sum of x variables equals to 1. What does it mean? It means that each person should be accompanied with just one person, one airport worker. And the middle one is the most beautiful one because, well, some jobs are incompatible. What do I mean? I mean that, let's do a concrete case. If the work shift is 8 hours and I assign to a worker a job starting at 10, I can't give the same worker a job ending at 7 p.m. because it would be 9 hours apart. And of course, these two jobs are said to be incompatible, or they are even incompatible if they overlap, like one job from 2 to 4 and the other from 3 to 6. They overlap. They cannot be assigned to the same worker. Of course, it cannot be in two different places at the same time. So all the incompatibilities are modeled in that middle line of two variables having the same worker. Just one of the two can be 1, or maybe no one of them if the solution is different. This is a mathematical model of this big airport scheduling, this big, we can say it's a human resource allocation problem, if you prefer, but we call it a tactical fixed job scheduling problem with spread time constraints. Spread time here is the work shift. Next slide. I created an algorithm to solve this in less than 2/10 of a second. It scheduled a whole workday with even 2,000 assistances to be scheduled. It's based on criteria related to the flexibility, so the different languages the workers can speak. And it's a procedural, greedy algorithm. That's why it's so quick, but it is also very effective. Next slide. We know that in 2/10 of a second, it can, respecting all the rules, provide a top quality service, respecting all the rules, but it is even very efficient because it allows the airport to use less workers than the ones we use today, even in some cases 20-25% less, and generally about 16% less, which is a lot. It allows for more duty rotation as these workers are not only hired to accompany blind people, but even to do trainings and to take bookings and to do many other things. So, as you can see, maths modeling provides an efficient solution, a good quality, a top quality solution that respects all the rules of workers and of passengers with special needs who ask for assistance, and does it not only in fashionable style, I might say, but even in a very efficient way. This is that's been my first publication and the core of my PhD thesis some years ago. So I'm very proud of it, and it will be implemented in some airports in 3 different nations from this summer. So I want to stress a little point. I modeled it because I knew what blind people face when traveling. And so here, I not only can abstract from the concrete case, I know the concrete case myself, but I could abstract from a concrete case to a problem, the TFJSS, the tactical fixed job scheduling with spread time constraint, that had only, until now, industrial applications. That's the power of mathematical modeling. That's the power of, I would say, blind mathematical modeling. And so I want to give you just a last insight into my research. With my research group, we have been contacted by the Ministry of Schools in Norway. They wanted an algorithm to schedule the external external candidate exams for the whole of Norway, starting from the county of Westfold in south of Norway, and then for the whole of Norway. For this purpose, you can imagine there are a lot of technical, logical, location-related constraints, not only for students, but for the more than 3,000 people involved. So not only students, but teachers, censors, school personnel, and more. The model for this problem is huge. It would need like 30 minutes only to explain the more than 20 sets of constraints and the different sets of variables we had to create. But I can tell you that our algorithm has been, our model and our cut and branch algorithm has been used successfully and accepted by the ministry, who scheduled already 4 exam sessions with our algorithm. The algorithm is a cut and branch, so it's based on cuts. Next slide, the last but one slide. The boredom is always ended. I can tell you that my job in the research group came because I'm blind. Because when you, even in the previous case, I didn't tell it to make it, more readable. But what we do when we create a mathematical model is creating a polytope or a polyhedron in n dimensions, where n is the number of variables we have. So it's a huge and impossible to see geometrical figure. But if one cannot see, visually a figure in 4 dimensions, one can see it in his or her mind. And my duty was to find, my job in this case was to visualize this geometrical figure, and particularly to find cutting planes or valid inequalities, if you prefer. It means that when we create these polytopes, the the acceptable, we say the feasible solutions are on some of the vertices of this big polytope. And so even the optimals are on some, a very limited number of these vertices. My job was to find geometrical and algebraic objects we call valid inequalities, like the one you see on the top. I hope you can see it. And these are just representing big hyperplanes. Like if we have n dimensions, this is at most n minus 1 figure, geometrical entity that cuts a part of the polytope, a part of the polytope which is useless because it doesn't contain feasible solutions. So the algorithm, the branch and bound algorithm, who jumps in a particular way from a vertex to another one to find feasible or potentially optimal solutions, completely ignores a part of the polyhedron of the polytope, which is made useless because it cut away by these big, almost invisible for sighted people, geometric entities, valid inequalities or cuts, just, on, we call them cuts normally. Valid inequalities is a kind of a formal term. And I'm very happy to say that this work has been published on the most prestigious journal, or one of the most prestigious journals for scheduling, published by Springer, which is the Journal of Scheduling, a couple of months ago, at the beginning of February this year. We have seen blind people throughout history. This afternoon, this evening for me, we have seen blind people modeling the world. We have seen people modeling educational devices, mathematical objects, equation full of beauty and elegance, solutions to technical problems, solutions to human resource allocation problems. This should be enough to understand why blind people can really make a difference in science. Um, and I might say, I'm very flattered by your invite, even to tell a bit of my research in such a prestigious event, such a prestigious talk series in such a great university. Thank you for listening. Last slide. Those are my contacts. I'm here for all your questions, and thanks again for inviting me.
Wow,
Thank you so much for coming.
Yeah, thank you so much for presenting and sharing your knowledge with us. It was really interesting to learn how math is really involved with everything from like the 1800s to today with the airport. I thought it was really interesting how you
And it's
connected with.
very important to understand that if you take the list of blind scientists in history, in the past, before assistive technologies were improved, the vast majority of them were mathematicians, because the abstraction power that blind people can have following different patterns should not be like, it's huge. It should not be underestimated. It's not a case that we have so many important mathematical results from blind people in history, even related to geometry. I'm thinking even to Bertrand Morin, the China-born but French mathematician who solved the inversion of the sphere problem in the most elegant way in the 1960s. I think it should be 1967, something like that. The inversion of the sphere problem It's a standard, very famous geometry problem, which is to turn a sphere inside out, like a spherical surface inside out, with the inner and the outer part exchanged with a single transformation. It is, a very important result that is, we owe to a blind mathematician.
Yeah, I think what you just talked about, I want to mention something that was really memorable from your presentation was that Euler, who was considered to be one of the people that can't understand visual beauty, came up with the most beautiful math equation.
It's not a case, I think. It's not a case. It's just following a different path, a mental pattern. And well, just a little deviation. We know that even ancient cultures, like the ancient people of Finland before the Vikings arrived, thought that blind people should be like, they were not Christians at that time. I'd say like pagan priests, like druids, because thanks to their different ability to perceive the world, they could be in contact with gods, and understand beauty in a different way, in a more concrete way.
Thank you for that. I want to open it up to any questions. We have a question here.
This is Deron. I'm a student at Northeastern University, actually. I just wanted to ask you a question, Dr. Michelle. It is right. All right.
Michele, Michele is the pronunciation, but
Michelle.
it's typical. It's typical. No worries.
All right. So, my question was like, what is the most like important math language out of algebra, calculus, trigonometry, geometry, and I think quantitative reasoning, in your opinion?
Well, I don't think they are different languages. They are all part of a big, articulated, complex language that explains our universe to the infinitely big from the extremely small. I don't think there's a standard like language which is better than the others. And I say this, well, in the 18th century, there would be people like physically fighting to to answer, to prevail on others with their answers to this question. But I can tell you that if I have to point something out, I would say that is, in general, is discrete mathematics, because nature is not continuous. Nature is discrete. The number of molecules, atoms, electrons in the universe is immense, but it's finite. It's curious, but it's still finite. So even a lot of big analysis problems that are on the continuous, like for functions or even in combinatorial optimization, in optimization, in operations research, sometimes there are linear programs or non-linear programs that are continuous and they get discretized, is maybe the right word. They are turned into discrete discrete problems, because it's, I would say it's more natural for humans to think in discrete, but at the same time, it's probably the most immediate mathematical language. I think that even successions, the base for analysis, that one of the first things we work on when we study analysis, and series and combinatorics and graphs, many important branches of mathematics are actually based on a discrete approach, discrete sets.
I have a question about the application of your algorithm in airports. So math is so beautiful and perfect, but people are not. So what are you expecting? Where are you expecting it to fail? What will be the limit?
Or have you modeled in human error?
Okay, the human error might be modeled probabilistically.
Yeah.
I mean that even like a plane is slightly delayed, this can be done. This can be done. I had it in my plans, but I changed institution. I passed from the University of Naples, from the University of Sannio, and then got absorbed in other things. Consider that people that generally work on combinatorial optimization do not work a lot with probabilistic, but only with deterministic problems. But at the same time, there are problems. I can tell you that it happens a lot with scheduling, rescheduling, rerouting trains in case of mass disruptions, big disruptions. There are standalone models that are concerning the rescheduling in case of a disruption of an already scheduled problem. So it should be like, there should be another model that comes in place and solves the rescheduling problem, the reorganization problems, if human error or like just random chaos intervenes.
Well, is that your next project?
Not at the moment, but it's one of the ideas. At the moment, I'm working on a very, very huge mathematical model, which is the binary knapsack problem. We are very close to a huge conclusion. Fingers crossed, and we'll see. We'll see. I hope this video will age well.
Are there any other questions or comments anyone would like to share?
I also have a question.
Of course.
Okay, so hi, I'm Cindy. I have a question for you, Dr. Michele. So I really impressed about your formula to apply in the airport. So I'm wondering like whether that formula can also be applied to other means of transportations like trams, buses, and subways, because I feel like it would be very helpful for people with visual.
Okay. It can be done, but consider this. Even a very big station, railway station, has a limited space compared to an airport. And it's generally more handy. I mean that you can do this, but computationally it's much, much easier. I mean, you don't have, at least in Italy, I don't know how it works outside of here, but you never get 2,000 accompaniments in one day. Even the biggest stations can have 30, 50, 70. That can be solved even like in 3-5 milliseconds.
Oh, I see.
With the same algorithm. So it's not really challenging from the combinatorial point of view, because as I told you, I cannot find the optimal solution of this problem because it would require too much time. It's a NP complete, even a NP hard problem. So no optimal solution in human times. So what I did is to produce a suboptimal solution that in this case must be compared or to other algorithms to solve the same problem, or to a real world scenario like I did in this case, because I was the first to do this. Other projects of the same on the same problem were focusing on like customer satisfaction, like I can avoid this rule and let's see how it impacts customer satisfaction. Like I can worsen the quality without changing the overall rate a lot. And this is wrong because you have by law to offer the best possible service.
Thank you so much for your answer.
As I was saying, big instances are more interesting for us. That's why I went for the airports. But yeah, it can be applied even in big railway stations, but it would be like very, in many stations, I would say 99% of stations around the world, you can find the optimum solution in 2 minutes with pen and paper, with like 10, 20 accompaniments per day. It's different in airports when you can have 500, 1,000, 2,000 accompaniments per day.
Any other last comments or questions?
I would like to, Michele, it was a fantastic talk. Thank you so much for your time. And I believe are you gonna tell him about, we're gonna be mailing you some
yes.
allied. Go ahead.
Yeah, Michele, just for a little token of appreciation, we have a set of our merch for Allied. We will be mailing that to you, so you'll have a little nice surprise in your mailbox.
Thanks.
the
Thanks.
Yes,
Thanks. So I can put some of them in my office behind my or on my desk, so to like I can brag a bit.
Yes, totally.
Thank you so much. Thank you.
Appreciate you.
Thank you for inviting me. Thank you for your patience.